Magnetic Dipole Fields, Lab 9. Tiffany K., Tiffany O., Joanna R. For our magnetic dipole field lab, we explored distance dependence of magnetic fields due to a small bar magnet. This allowed us to compare them to given equations for both parallel and perpendicular magnetic fields. For magnetic fields specifically, an application on our smartphones that included a magnetometer chip assisted us in navigating exactly where the magnetic field is due to a permanent dipole magnet. With a proper alignment and all disruptive fields out of the way, we would find that the magnetic dipole moment would fall at 2.51 times 10 to the negative 1 meters squared. Then with further calculations, equivalent solenoids and electron alignments were discovered. The required tools needed to complete this experiment included a smartphone with a magnetometer sensor, a bar magnet, a metric ruler, a magnetometer application, which for us was Firefox, a flat surface, several pieces of tape, and the associated lab spreadsheet. One important element to note while performing this experiment is the importance of finding north. Since Earth has a magnetic field, we must account for it, and therefore find it by using the bar magnet and making sure it is perpendicular to Earth's magnetic field. With this in mind, it will allow us to find proper alignment in regards to latitude and longitude, and therefore ensure all readings are not including disruptive fields. For us to achieve this, we had to lay our smartphone upon the flat surface and rotate it until the Z component of the magnetometer was close to 0.
To find the location of the magnetometer chip, we placed both the ruler and bar magnet in the east to west direction. To find the sensor along the X direction, we gently slid the phone up and down without rotating it. Once the X component on the Firefox app was at its maximum and the Y component was at its minimum, we placed a piece of tape along the width of the phone to indicate the line in which the sensor was located. To find the sensor along the Y direction, we rotated the phone 90 degrees and repeated the same steps. Only this time we placed a second piece of tape along the length of the phone when the Y component on the Firefox app was at its maximum and the X component was at its minimum. To measure the magnetic field of the bar magnet parallel to the axis of the dipole, we had to ensure that the phone was aligned with the north and that the bar magnet was parallel to the ruler and centered with the phone. We took measurements at 8, 11, 14, 17, 20, and 23 centimeters. After taking these measurements, we input them onto a spreadsheet which created a graph. From this graph, we can see that the magnetic field of a dipole decreases as distance from that dipole is increased, which can suggest an inverse relationship between these two. To measure the magnetic field perpendicular to the axis of the dipole, we follow the same procedure as before, only turning the magnet 90 degrees this time. As you can see in the picture, when we first did this part of the experiment, we also turned the phone 90 degrees, which gave us inaccurate measurements. So when we tried it a second time without turning the phone 90 degrees, we got better measurements, which we input onto the spreadsheet and got a graph that looks similar to the one as before, showing an inverse relationship between magnetic field strength and distance. From the spreadsheet, we also got an estimate of M to be 2.51 times 10 to the negative 1 amp meters squared.
Okay, the first thing we need to do is find our area and then find our current for this magnet. So measure your magnet. You're going to find the radius to be about 0.002 meters of the magnet, and then you should get your area to be about what here I have on the screen. And then using that, we're going to use the mass equals number of loops times current times area. You're going to deconstruct that formula to find the current. So I have written out, you're going to make it I equals M over NA, and we only loop around one time for right now. We're going to assume the wire only goes around one time, so that number should be 1. So you should find this first current to be about 20,833 amps. So now we're going to find the current if we're going to use a 14 gauge wire going around the loop. So first we need to figure out how many times this wire would wrap around this magnet. So the diameter of this wire is 1.63 millimeters. So first you need to measure the length of the magnet, and you're going to divide the length of the magnet by the diameter. So that's the thickness of the wire over the thickness of the length of the magnet, and see how many times that wire can fit. you should get 6 times. So now that we know that this wire can wrap around our magnet 6 times, you're going to use N equals 6, and you're going to do the same thing as before, and you're going to find the new current for this wire that wraps around it, and it should be about 3,472 amps. Okay, now that we've calculated for our current, we're going to determine the percentage of the electrons with their dipole moment pointing in the same direction as the magnets. So for this experiment, we're going to assume that this is going to be about 9.27, 10 to the negative 24 amp meters squared, and due to the number n valence electrons spinning in the direction. So we're going to assume that there's only one valence electron per atom. This is going to be the dipole moment of one electron, so just set it up. Number of electrons pointing in the same direction in spinning up, and the number of pointing in spinning down. And then we're going to find the dipole moment, which is this little formula right here, n spinning up minus n spinning down times micro b. And then the total of number of electrons is going to equal n equals n spin up plus n spin down. So let's go ahead and solve for those. Okay, so we're going to find the valence electrons now, assuming that there's only one valence electron per atom. So the length of an atom is this number right here, 1 to 10 times 10 to the negative 10 meters. So to find the volume, you're going to do this number cubed. So the volume is going to be 1 times 10 to the negative 30 meters for the volume of an atom. Now you're going to find the volume of the magnet using pi r squared times height. We found it to be 1.26 e to the negative 7 meters cubed. And now to find how many cubes, or how many atoms, in other words, can fit into the magnet, you're going to divide the volume of the magnet, so the bigger number, by the volume of the atom, the smaller number. And that's going to give you a really large number because there's a lot of atoms in this magnet, right? So it's going to give you 1.26 times 10 to the 23 atoms are in this magnet. Okay, so those formulas that we talked about earlier, we're going to use system of equations, so you might have seen this in algebra class or something, to find the number of dipoles spinning up, spinning down, and then the ratio of spinning up to total number of these electrons, right? So we have those two formulas here, n spin up plus n spin down equals n, and you also have the n spins up micro electron field minus the n spin down of the micro b, and that's from the other slide from earlier. That's our constant, equals n, right? So then you're going to format this formula, and that formula is going to get you 2 spin up equals n plus m divided by ub, and then you're going to get that formula to equal n spin up equals n plus mub divided by 2. And then last but not least, the formula n spin up over n is equal to 1 plus m over n ub divided by 2. So these are the formulas that you're going to use after deriving them in order to find these ratios. So using those three formulas, you're going to find those three different things. So these are the numbers at the bottom of the screen. N spin up, the ratio we found for that was 0.61 electrons. The n spin up was 7.64 e to the 22 electrons, and the n spin down, the dipoles, for that is 4.96 e to the negative, or e to 22 electrons. So basically there's a lot more dipoles pointing in the up direction than the down direction is what we found in this magnet. And the ratio is just a little bit over a half.
By performing this experiment, we were able to discover that with regards to Earth's magnetic field and by eliminating disruptive fields, the distance of dipoles increases while the magnetic field of the dipole decreases. Our calculations indicated that the magnetic dipole moment of our experiment fell at 2.51 times 10 to the negative 1 ammeters squared. With all of this in mind, we were able to compare it to predicted equations found in our group problem sessions to compare just how accurate our readings were.